central collisions of heavy nuclei. The nuclei break up, and there are many products that come out. And the observables that we discussed so far were actually ones which could have been done without seeing all particles at once. You just could see one particle at a time, and figure out what the spectral distribution for that particle were, and by integrating over all angles, you could figure out the yields. So far we looked at the so-called single particle observables, which you could study using just a telescope, and maybe some trigger for centrality or something like that. So far, single particle, we look at single particle distributions and yields. Now, when there are many particles coming out, there should be, intuitively you expect there should be some information in investigating how particles influence each other in emission. So we'll look at that question now. Mutual influence of emitted particles on each other. Emitted particles on each other. So some of that we actually was already contained in some data that we discussed. Sort of implicitly. So for example, we looked at how particles get distributed in transverse momentum versus rapidity. And you have this target region, projectile region. If you look at the vicinity close to a projectile, and there's a projectile residue that survives, you see the so-called Coulomb bridge, which is sort of a shell around the presumed location of the projectile residue. And you can imagine that this is this shell. So here the probability of finding particles is low. Outside of the ridge, it's low again. And over here, it's high. And you can imagine that this ridge is due to the fact that, let's say you have some residue, it emits particles, and when particles get emitted, they get emitted at low velocity relative to the projectile, but then they are charged and they are repelled by the projectile, and over time they acquire finite velocity. So this velocity is due to the Coulomb boost, and they can never get too close to the projectile, because if they were emitted close, they would be anyway repelled. Okay, so there is a Coulomb boost. Now, however, you have other sources of particles. So you have a central source, which is a region. You can imagine that projectile flies this way, target residue flies out this way. Somewhere there you have central source that emits. As far as the central source is concerned, you may have some particles that by accident drift into the region of velocity which is close to the projectile. Okay. But if they are far away from the projectile, they start far away, there will never be enough Coulomb repulsion to basically move those particles away from that region, because to move away you need to be emitted close. So these particles may contaminate that region and wander in if they come from a different source. Okay? So central source can contaminate Coulomb hole. So what we can see here is in the emission, actually, projectile residue affects particles if they are close enough in space when they get created, but it will not affect particles which will be emitted farther away. And sort of, it's a general conclusion from this. You may think, okay, I can look at how different fragments get emitted from the reaction, and I can look whether they impact each other or not. If, let's say, there is a Coulomb repulsion between them, if they get emitted from some region which is concentrated, some region which is concentrated in space, they will be repelling each other. They cannot come close to each other in velocity. But if they are emitted farther away from each other, then they don't care about each other. Okay, so you can look at particle correlations, and so you can construct a so-called correlation function. And the correlation function will be you construct it. So it's a function of velocities of the two particles. Okay, and it's you construct it as a ratio of probability of observing particles at respective velocities v1 and v2, divided by probability of observing single particle at velocity v1 times probability of observing the other particle at velocity v2. And if the particles don't care about each other in emission, if emission is uncorrelated, no influence, then you expect this correlation function. So you expect P2 of V1, V2 being simply a product of P1, V1 times P2, V2. So one particle doesn't care about the other, okay? And then this correlation function should be 1, okay? There are different ways of constructing this probability. There's a whole literature. You mix events, sort of, because if you take particles from different events, then of course one event does not have an influence on the other. So you can construct this uncorrelated, unbiased emission from that. And generally, you normalize if velocities are very different, then if there are many particles emitted, they don't care about each other. So this should go to 1, no matter what, when velocities are far away from each other. V1 minus V2 large. Okay. So when you look at this kind of so constructed correlations, usually this is what you find at large relative velocities. Very often, deviations from one occur. When V1 minus V2 goes to 0. Okay, so let's look at an example. So this is, the reaction is argon plus gold at 50 MeV per nucleon. This is the correlation function, C of V reduced, which stands for V relative. Okay, the fragments are so-called intermediate mass fragments. These are fragments with Z between 4 and 9. The main author is Glassmacher. And if you go to large relative velocities, then the fragments don't care about each other. Okay. Then you see that if fragments are emitted at close relative velocities to each, with a small separation of relative velocities, the probability of finding such fragments is suppressed, okay? Which means that these fragments tend to be emitted from some compact source, and maybe over a short time, because if, again, the time plays a role, because if the fragments are emitted over a long time, then one of them can move away from the source, and then if the other comes, it will not impact the other. So it's the time and space are mixed. The solid lines show simulations, and the simulations assume emission from a source which has radius 7 Fermis. These IMF fragments are emitted just from the surface, isotropically. The source is giving a lifetime, so emission, the times of emission are sampled according to distribution in time, which is e to the minus t over tau, where tau is the 75 Fermis over c. The calculation is done actually assuming classical motion for the fragments and just classical trajectory simulation. Okay. So as fragments are emitted, they affect each other. In fact, the source also affects the source is given some kind of charge and is assumed to, so you can see that the most radical assumption is that source has the charge of gold and assumes the emission. Okay? And as you can see, the simulation reasonably reproduces the data. There is one qualitative aspect here. This simulation here predicts that there will be no fragments with very low relative velocity. The data seem to show something, and this you may think is a contamination which stems from some fragments breaking up later. And when something breaks up later, it can go into this hole and contaminate it, okay, fill it up, just like the central source can in this sketched rapidity plot could contaminate. Okay. Now, in general, if you write a probability for finding fragments, a classical probability for finding fragments at velocity v1, v2 at detectors, you can write this as an integral over all emission points at the source. So write it d3 r1 at the source, d3 r2 at the source. These are two fragments emitted with some velocities v1 at the source, v2 at the source. I'll integrate it. Some of the integrations may be just deltas. Maybe integrate. Some of the integrations may be integrating deltas. But you sum up over all kinds of positions of emission, all kinds of velocities at emission time, probability that the source emitted fragments at location r1, r2, velocity v1, source, v2 source. And then you will have a classical transformation. I'll just write it from r1, r2 at the source, v1 at the source, v2 at the source. This is according to classical equations of motion to positions at infinity, relative positions at infinity, r1, r2, at the time where you started them at infinity with some velocities v1, v2. And you, maybe the positions at infinity will suppress. We are just interested that they are at v1, v2. Okay. So this is, in the simulation that I've shown you, this is actually, this transformation is done using classical equations of motion. Now, if you wanted to describe the problem quantally, you would need to solve the quantum problem of motion. So you would need to solve the Schrödinger equation. And generally, the Schrödinger equation, if you want to account for influence of every particle on every particle as they move towards the detector, is hard. But let's say that you ignore most of the influences and you are only interested in an influence of the two fragments that go towards the detector on each other. Okay? Of two fragments on each other. Then the Schrödinger equation that you need to solve is just a two-body Schrödinger equation. And since the motion of the center of mass is trivial, you only need to solve the Schrödinger equation in relative motion of the two fragments. And that becomes one-body Schrödinger equation. So this is something you can do And in this kind of Schrödinger equation, you can include Coulomb interaction if if they are charged. Then you can include strong interactions. You can include anti-symmetrization, symmetrization, and so on. Okay, so this transformation is accounted by by a Schrödinger equation. If only impact of one fragment on another then two-body Schrödinger equation, but effectively one body. Then in this transformation, basically you transform, you connect the probability of finding two fragments at respect at V1, V2 by integrating the probability of particle emission at some positions with some velocities at the source position. This becomes, I'll just tell you, how it is in general. This becomes a density matrix that you form out of these wave functions. But if the source does not depend very strongly on separate velocities, so you can actually integrate over the relative velocity. And if you do the integration, this amount it becomes a modulus square of the wave function that comes out from the solution of the Schrödinger equation. So in the end, you get very simple expression if let's say this P emission source of V1 as V2 as is approximately just a function of one of them, of V, where V is overall velocity. Then this probability of finding particle at V1 at another at V2 becomes integral over emission at the source for the second particle, probability of emission at locations R1, R2S at net velocity V. This is the velocity of the pair times modulus square of the wave function at relative velocity V1 minus V2 and separation R1S minus R2S. So this begins to be so this shows you that what matters is how fragments are emitted relative to each other, and depending on the velocity, relative velocity of the two fragments as they go out towards the detector, they will be either they will have a lot of impact relative to each other or not. if these velocities, if the separation in velocity is large, this wave function, this is a scattering wave function, so when you take a modulus squared, on the average it will be 1. Okay, and there will be no influence of any structure in the source onto the probability of emission. So this is a scattering wave function. And at large V1 minus V2, this psi squared is, on the average, is 1. There may be some interference effects or symmetrization effects, but even if they are there, it will be quick oscillation that will average out to 1. So if you have when you have this kind of expression, basically the left-hand side is supposed to describe data. This probability of emission at different positions for different velocities is something you don't know. This is that's some information you can gain about the reaction. On spatial distribution. I suppressed time here. Time is basically hidden in those R1s and R2s. You need to consider those in the rest frame of the emitting of the two-body system that goes out to the detectors. On spatial extent of the reaction. This is something you know how to calculate. So in the end, this you determine in the experiment. This you can calculate. This is usually what you fit in order to describe the data. Okay, and what you try to learn is basically what is the distribution of emission points. Okay, so at some level you can take photographs of reactions. Okay, so how does it work? So, for example, let's take the case of Coulomb repulsion. So let's imagine that you have an emission source and it has some distribution in R1 minus R2 at source. Okay. So okay. So you can assume it's a surface, it's a Gaussian, it's a rectangular box or something. Now here you have wave function. And again, this is a function of the separation at emission. Okay. For far away separations, it will always go to 1. For high velocities and high separations, it goes to 1. If relative velocity at low separations, if you have Coulomb repulsion, what will happen here with the wave function? So this kind of wave function describes a situation. Basically, it's a scattering process. You send two particles towards each other. They start at relative velocity v1 minus v2, and you ask what is the likelihood that particles will come at small separation separations relative to each other. 0. If it's a Coulomb, if you have Coulomb repulsion, there is a 0. And around 0, you have a Coulomb hole. And how big the hole is actually depends on relative velocity. If relative velocity is small, what can you say about this hole? If relative velocity is small, then of course, you imagine head-on Coulomb collision at low relative velocity or low relative energy, then they cannot come very close to each other. They return very quickly. So you will have something which looks like this. So this is low V1 minus V2, okay? On the other hand, if relative velocity is high, then they can come much closer towards each other. Okay? So depending on relative velocity, you will have a bigger hole or smaller hole. And then in this now quantile description of the probability of emission, rather than with classical equations of motion, you convolute this wave function with the source of some shape. So if the relative velocity is much bigger, if the relative velocity is small and this hole is bigger than the overall source, you will find no particles at that relative velocity, in the probability function, okay? Because you will be convoluting 0 with this distribution function. On the other hand, if you go to higher velocity, then you will have an overlap. And so in the quantile description, if you have the P V1 minus V2 as a function of V1 minus V2, low V1 here will be uncorrelated. I write it as PV1, PV2, but you can assume it's 1 for the sake of this consideration. So if you have low relative velocity, you get something like here. High relative velocity, you get something over there. Very high relative velocity will go like this, and you will get something over here. Okay? So in this way, you generate quantile at the same result, which you normally would, you would, in simpler consideration, you would generate classical. Okay. Now, when you have this quantum result, however, you have other possibilities. You have more. So if you have big fragments moving over large distances, interacting just with Coulomb, you can get away with classical description of their motion at low relative velocity. If you have protons which are interacting strongly, if you have particles which are interfere with each other because they are identical, you cannot get that classically, okay? But you can get it in quantum wave function. So gain is you can account for quantal phenomena in emission in transition from classical to quantal description. ability to account for properly for strong interactions, resonance phenomena, etc. For example, if you have, if you consider correlations of protons with each other, you have the following effects. You have Coulomb repulsion, strong attraction, with resonance, with lower energy resonance, and you have interference effects. So primarily suppression due to identity. So a proton-proton wave function as a function of separation would have, so if here we have one, would have Coulomb Hall, followed by resonance peak, and that peak can be very high, so it can be tens. And then you would have, at long distances, you will have oscillations due to the interference. You need to have spins aligned, so this is spin averaged. And when you fold this with the source, if relative velocity of the protons is very low, you will be predominantly you will have Coulomb Hall, no emission. If you increase the energy, this hall will shrink, resonance will come up, and then the correlation function as a function of relative velocity or relative momentum of the two protons will have behavior such that it's at low relative velocity, it's Coulomb. Then you have resonance peak. This is when this peak enters the source region, and then it will fall off and generate to 1. So let's look at data for proton-proton. So this is work by Kunde. The system is argon plus gold at 200 MeV per nucleon. So that's how much. Points are data. And the curves are various different types of theory. So the simplest theoretical description which they use is that probability of emission of a proton relative to the center of the source is just an exponential of minus R1 source squared, so just Gaussian form for each of the protons. Gaussian emission shape for each proton. Okay, and they analyze the different brackets of energy of the two protons. And as you can see, they see a variation of the emission source, so between 5.5 Fermis to 6 Fermis. They also have some transport model predictions, and there is so in this figure there is it looks like the transport theory gives rise to two sharp sources, two compact sources. But at that time when the analysis was made, there was no, people tried to have one such source and try to describe everything, and they were missing the point is that reality is more like you have a big reaction region. Many things happen in that region, so this is in space. Different things are emitted. If you look at the proton-proton correlation, you see a compact object that emits particles and gives rise to the correlation which you see, but that compact object is immersed in a background which is more mundane and spread out. Okay? So if you take that into account, then these models are capable of describing this. This is the similar situation as where I mentioned, that the central source can fill the hole, the Coulomb hole. The same way basically this emission will give rise to uncorrelated emission, and if you want to compare this to that, you need to subtract one and then compare the shape of the deviation from one for the two, so roughly. So this analysis misses background. Okay. Questions, comments? Go ahead. When you write the wave function for the correlated two particles, why you only consider the scattering between the two particles? Why you didn't receive the contribution from the source to the other part? this convolution becomes very easy. And this is in the case of, so easy case of correlation. This is the case of interference in pion emission. So pions, if you have, this is relevant for high energies. So consider a situation we have some kind of emission source, and consider two identical pions. So if they are charged, they would be Coulomb repulsion, but actually the impact of Coulomb repulsion is limited to a narrow range of relative velocities, and people tend to correct for that. I mean, they just calculate it correct for that, and then they just leave this identity interference. So what is this identity interference? So let's say that you have emission from point R1 at the source and R2 at the source, and you observe pion with momentum, let's say P1, and pion with momentum P2. And you have two options. The pion with momentum P1 could come from R1 point, P2 could come from the R2 point, or you could have P1 coming from R2 and P2 from R1, okay? Then the wave function P1, P2, R1 source, R2 source squared will be modulus square of 1 over square root of 2 just symmetrized wave function e to the I P1 R1 S e to the I just plane waves P2 R2 S plus e to the I P2 R1S e to the I P1 R2S. Okay, modulus squared. So this will be 1/2. And so let me still write it one more time here, e to the I. No, I will not. Okay, now if I take this modulus square, calculate this modulus square, what do I get out of it? If I square this, what do I get? If I square my exponential, take modulus square of exponential 1, okay. This one, what do I get? 1 again. What about the interference? plus. So I have this times conjugate that. So I have e to the IP1 R1 s e to the IP2 R2s, and this conjugate e to the minus IP2 R1s e to the minus IP1 R2s. Then this plus this, which will be EIP2 R1s e to the IP1 R2s times this conjugate e to the minus IP1 R1s e to the minus IP2 R2s. That's it. So this is 1/2 2 plus here I have e to the IP1 times R1s minus R2s minus IP2 R1s minus R2s e to the IP2 R1 minus R2 minus IP1 R1 minus R2, which is 1/2 2 plus e to the IP1 minus P2 R1 minus R2. I'll drop those S's since we don't have R without S's, and then the conjugate. So this becomes 1 plus, and this is 2 cosine P1 minus P2 R1 minus R2. Okay? And the probability of finding the particles respectively at P1, P2 becomes integral d3 R1, d3 R2. This probability of emission, R1, R2, times 1 plus 2 cosine P1 minus P2 R1 minus R2. Okay. So if we just had the 1, this is actually a situation without interference, which you get 1. Then this probability does not depend on P1 and P2. Okay? And if you normalize it properly, this gives an independent emission. Okay? And this gives you the influence of interference in emission between the two particles as they go out towards the detectors. And that interference term depends on the separation between the emission points. And in this case, this modulus, which is this modulus squared, you can plot it as a function of R1 minus R2 or P1 minus P2. So if R1 goes to I should have no 2 over here. If R1 goes minus R2 goes to 0, then this goes to 2. Then if it moves, let's say, along P1 minus P2, it will oscillate, and it will oscillate in this kind of fashion, where this width goes like 1 over P1 minus P2. Okay? And then you take some kind of source. The source, if it fits into this maximum, you will have big correlation. If the source covers many maxima and minima, then this will average to 0. You can notice here that there is no dependence on the average position. R1 plus R2 over 2 can be integrated out. We can write this further as, so we can replace D3 R1, D3 R2 by D3 R1 minus R2, D3 R1 plus R2 over 2, and in the end write this emission probability, this detection probability at P1 and P2 as D3 R1 minus R2, probability of emission at R1 minus R2 relative to each other times 1 plus cosine P1 minus P2 vector R1 minus R2 vector. Okay. Very often what people assume about this emission source, or the simplest assumption that you can make, is that this emission source is a Gaussian. So let's say that let's assume that shape of the emission source for individual pion goes like exponential of R1 minus R1 squared over R0 squared. Then from the convolution over overall position of the center of emission for the two, you get the relative source, which goes like exponential with twice the width. Sorry, R1 minus R2 squared over 2R0 squared. And then probability of finding them, the pions at P1 and P2, goes like integral of D3 R1 minus R2 exponential of R1 minus R2 squared over 2R0 squared 1 plus cosine P1 minus P2 R1 minus R2. And each of, so cosine consists of two exponentials, one with a plus, one with a minus in the argument. And each of them actually gives the same Fourier transform. It amounts to a Fourier transform of this source. And what you get in the end is that P1 plus P2 will go like, from this you get 1 plus exponential of minus P1 minus P2 squared R0 squared think over 2. That's it. Okay. So the correlation function has the form 1, P1 minus P2, starts with 2, and then falls to 0, and the width is proportional to the inverse size of the emitting source. Okay, yeah. So maybe just let me show the data. Unfortunately, I made I didn't write down where the data were coming from. This is presumably maybe a collision around 2 GeV per nucleon. And this is a Coulomb corrected correlation function, so the one of the type that we should study. So it goes into the vicinity of 2, and then falls down to 0, to 1. Sorry, the deviation goes from 1 goes to 0. And from here you can deduce the size of the source. So generally, the situation wherever you go with correlations is more compact source, more compact sources yield stronger correlations, because simply there's more chance of particles to impact each other in emission. Stronger correlations at small relative velocities. So conversely, if you know the strengths of the correlation, you can decide how compact was the emission zone in the reaction. Okay. So common finding is that these emission sizes depend on energy, depend on particle type, depend on energy of emitted particle, depend on energy of the beam, and so on and so on. It's a tool.